Nobody ever asks the easy questions in the dark. You go outside, you look up, and the first thing that happens, if you're paying attention, if you haven't completely insulated yourself from the actual experience of existing on a planet, the first thing that happens is you feel it. That pull, that almost gravitational weight of the question you have been trained since childhood not to ask too hard. You look at all of it, the stars, the Milky Way, the sheer impossible depth of a sky that goes on in every direction, and the question arrives unbidden, unwelcome, and completely unavoidable. What is out there at the very end? What is beyond all of it? Not beyond the stars, not beyond the galaxies, beyond space itself. And right there, before you've even finished forming the question, you run into the first wall. Because beyond space, that phrase already contains a hidden assumption so deep and so stubborn that most people never notice they've made it. You're imagining, aren't you, that space is a thing sitting inside something larger, a container inside a container, a bubble inside a room. And your intuition is telling you that the room must exist, that there must be an outside, that walls require beyond by definition. Your intuition has served you well your entire life. It has helped you navigate hallways, catch objects thrown at you, judge the distance to the horizon. It has been built by evolution over hundreds of millions of years to operate in exactly one regime, the regime of ordinary human scales, ordinary human speeds, ordinary human experience. And in this particular question, your intuition is absolutely, spectacularly wrong. So let's do something uncomfortable together. Let's take everything you think you know about the geometry of existence, lay it out on the table, and look at it honestly. Because I promise you, and I've been thinking about this question for most of my professional life, from the moment I first started seriously grappling with cosmology as a young man at the University of Chicago, I promise you that what is actually true is so strange, so counterintuitive, and so much more interesting than the cartoon version that it would be a genuine crime to hand you anything less than the real thing tonight. Let me start with something that sounds simple and isn't. When we talk about space, what do we actually mean? In the Newtonian picture, which governed physics for roughly 2.5 centuries and which still governs most people's mental model of reality, space is the stage. It is the fixed, absolute, eternal backdrop against which things happen. Objects sit in it, move through it, exert forces across it. The space itself, however, is passive. It doesn't participate, it doesn't bend, it doesn't stretch. It just is, uniformly everywhere the same. Newton believed this so deeply that it was barely even a belief. It was a foundational axiom, for as unquestionable as the axiom that mathematics is consistent or that a thing cannot both exist and not exist at the same time. And then in the early 20th century, Albert Einstein, who was, let me be clear, the most extraordinary scientific mind in the last 4 centuries, possibly the most extraordinary since Newton himself, Einstein, sat down and dismantled the stage. What he discovered through years of work that he himself described as the greatest intellectual struggle of his life was that space and time are not the passive background of physics. They are physics. They are physical, dynamic, malleable objects. They respond to mass and energy. They curve, they stretch, they can propagate waves, they can in principle be torn. The geometry of space-time is not a fixed coordinate system you pour matter into. It is an active participant in the story of the universe, constantly negotiating its own shape with everything that exists inside it. This matters for our question, what is beyond space? Because once you accept that space is a physical thing rather than a metaphysical, given the question of what lies beyond it changes character entirely. You are no longer asking what is outside the container. You are asking what is outside the thing itself. And that is a very different question. Here's a thought experiment. I want you to imagine the surface of a sphere. Not the sphere, the surface, the two-dimensional skin of it. Now, suppose you are a creature who lives entirely in that surface. You are two-dimensional. You can move north and south, east and west, but the concept of in or out, of depth, of a third dimension perpendicular to your surface, none of that exists in your experience. You can walk in any direction forever and never hit a wall, never reach an edge, because there is no edge. The surface is finite. It has a definite area, but it is unbounded. There is no boundary. There is no wall. And if someone asks you what is beyond your space, they are asking a question that has no answer in your physics. The beyond is a direction that doesn't exist within your geometry. The sphere exists in a higher dimensional embedding space, yes, but there is no physical reason your universe must have an outside just because it has a finite size. No physical law says that a finite thing must be contained in something larger. Now scale that up. Our universe may be the three-dimensional analog of that spherical surface, finite in volume, but with no boundary, no edge, no wall you could ever reach. Or it may be infinite. We do not know. And this is not a statement of intellectual inadequacy. It is a statement about the genuine limits of what observation can reach. And I want to be precise about why. There is something called the observable universe. It is a sphere centered on Earth, or rather centered on wherever you happen to be, because every point in the universe is at the center of its own observable sphere. The radius of that sphere is approximately 46 billion light years. Not 13.8 billion, which is the age of the universe in years. That number trips people up. The universe has been expanding the whole time light has been traveling, so the objects we are seeing at the edge of our observable sphere, the objects whose ancient light is just now arriving at our telescopes, are now actually much farther away than 13.8 billion light years, roughly 46 billion. This is a finite, knowable number. The observable universe is large beyond easy comprehension, containing something in the neighborhood of 2 trillion galaxies, each containing hundreds of billions of stars, but it is bounded, and its bound is set not by the structure of space, but by the finite speed of light combined with the finite age of the universe. What is beyond the observable universe? Almost certainly more universe. The same kind of thing, arranged the same way. Galaxies and stars and planets and the void between them, extending outward to a distance we cannot see and may never see, because the light from those regions has not yet had time to reach us, or in some cases can never reach us, because space between us and them is expanding faster than light can travel through it. Let me say that again because it sounds wrong and it is absolutely correct. There are regions of space from which light will never reach us, not because anything is moving faster than light, but because the space between us and those regions is itself expanding, and that expansion carries those regions away from us faster than any signal can cross the growing distance. They exist, they are real, they are part of the same universe, and we will never see them. This is already strange. But here's where it gets stranger. The expansion of the universe, the thing Edwin Hubble confirmed observationally in 1929, the thing that Georges Lemaitre had already predicted from Einstein's equations in 1927, to rather less fanfare than he deserved. This expansion is not matter, flying apart through space like shrapnel from a bomb. This is the error almost everyone makes the first time, and I made it too, briefly, before I understood what the mathematics was actually saying. The galaxies are not moving through space away from each other. Space itself is expanding. The fabric is growing. The distance between things is increasing, not because things are sailing off in some direction, but because the metric, the ruler that measures distance, is scaling up everywhere, simultaneously, at every point. Imagine a rubber balloon with dots drawn on it. Inflate the balloon. Every dot moves away from every other dot. No dot is at the center. No dot is moving through the rubber. It is the rubber itself that is stretching. That is, in rough form, what is happening to the universe. And it raises an immediate, deeply uncomfortable question that I think most textbooks handle rather badly. If space is expanding, what is it expanding into? And here I want to be completely honest with you, because honesty is the only thing I have to offer that is worth anything. The answer to that question is we do not know, And it is entirely possible that the question as posed is malformed. It may be that space is not expanding into anything. It may be that into is not a concept that applies to the expansion of space, just as north of the North Pole is not a direction that exists on the surface of the Earth. Space may simply be expanding full stop without there being any embedding space for it to expand into. But I want to be careful here because that is not the same as saying the question is meaningless. It might be meaningless, it might not. This is genuinely, honestly not resolved. Let me tell you about something that happened in 1979, because it changed how I thought about this question, and because the history of ideas matters. You cannot understand where we are unless you understand how we got here and how much of the path was paved with wrong turns. In 1979, a physicist named Alan Guth, who at the time was a postdoctoral researcher working on particle physics at SLAC, was wrestling with a completely different problem. He was trying to understand why the universe looks the same in every direction. Why, if you look at the cosmic microwave background radiation in one direction and then turn around and look in the opposite direction, those two patches of sky are at almost exactly the same temperature, even though they're separated by a distance so vast that in the standard Big Bang picture, they could never have been in contact with each other, never had time to exchange energy and equilibrate. This is called the horizon problem, and it is a genuine physical puzzle that the vanilla Big Bang model simply does not solve. Guth's solution, and I remember when it started circulating, the reaction in the community was first skepticism, then gradual grudging recognition that it worked far too well to be a coincidence, was inflation. The proposal that in the first tiny sliver of a second after the Big Bang, before a billionth of a billionth of a billionth of a second had elapsed, the universe underwent a period of absolutely explosive exponential expansion. Not the gentle decelerating expansion we see today, a runaway, violent, incomprehensibly rapid expansion driven by the energy of a quantum field, the inflaton, that caused space itself to double in size every tiny fraction of a second for somewhere between 20 and 60 doublings before it ended, and deposited all that energy into the hot plasma of particles that we call the ordinary Big Bang. What inflation implies for our question, what is beyond space, is this. If inflation is correct, the universe is almost certainly vastly, incomprehensibly, laughably larger than the observable universe. Not just twice as large, not even a billion times as large. The inflationary expansion almost guarantees that the totality of space dwarfs our observable patch by a factor so enormous that even the word enormous becomes misleading, because our language was built to handle numbers that fit inside a human life. The observable universe, all 2 trillion galaxies of it, may be to the full universe what a single atom is to the entire observable universe. And beyond that, in some versions of inflationary theory, the inflaton field didn't stop inflating everywhere at once. It stopped in our region but kept going in others, producing an endless roiling sea of inflating space with isolated pocket universes nucleating out of it like bubbles in an eternal boiling. This is the multiverse, and I want to talk about it honestly, which means telling you both why it might be true and why it gives serious scientists serious headaches. The eternal inflation scenario is not a piece of fringe speculation. It follows fairly naturally from inflation itself, which is in turn supported by several independent lines of observational evidence, the flatness of the observable universe's geometry, the specific pattern of temperature fluctuations in the cosmic microwave background, the large-scale structure of galactic distribution. These all match inflationary predictions with a precision that I find genuinely remarkable. So the framework has real support. The multiverse, in this sense, comes along for the ride. It is not something that was invented for philosophical reasons. It is a consequence of a theory that was invented for hard physical reasons. But here's the problem. The other pocket universes, the other bubbles in the eternal inflationary sea, are in principle permanently beyond our observable horizon. We cannot see them. We cannot send a signal to them. We cannot receive a signal from them. We might in principle, detect faint imprints in the cosmic microwave background from a collision between our bubble and a neighboring bubble. Some physicists have looked for this and found nothing conclusive so far. But in general, the multiverse is a prediction of a theory rather than something we can directly test. And that makes a lot of people uncomfortable, including, frankly, me. Not because the discomfort is evidence against it. Nature is not obligated to arrange things so that we can easily test them, but because we should be clear-eyed about the epistemic status of what we are claiming. Science lives and dies by the ability to test ideas. A theory that is permanently beyond test requires us to think very carefully about what it even means for it to be true. I want to tell you about a conversation I had many years ago with a colleague who shall remain nameless, a very fine physicist, who said to me, and I think this captures something important, Carl, the multiverse is either the most important idea in the history of science or the most elaborate, unfalsifiable story ever told. And the problem is, I cannot tell which. I've thought about that sentence a great deal. I still have not fully resolved it. Now, let's go somewhere even more vertiginous. We've been talking about what lies beyond space in the spatial sense, what's past the edge, what's outside the bubble, what exists in regions light can never reach us from. But there is another sense of beyond space, and it is the one that, when I am being fully honest, I find most unsettling in the most productive way. The question of where space came from. Because if you trace the expansion of the universe backward, run the movie in reverse, things get closer together, denser, hotter, run it back far enough, and you reach a state of infinite density and infinite temperature, the singularity, the Big Bang. And the equations of general relativity, which have been tested to extraordinary precision in every other domain we can reach, simply break down there. They stop making predictions. They output infinity, which in physics is not an answer but a flag, a signal that your theory has exceeded its own domain of validity and is telling you it needs to be replaced by something better. The singularity is not a thing inside the universe. It is a boundary of the theory itself. What this means, and I want you to feel the weight of this rather than letting it slide past as a technicality, is that the question, what happened before the Big Bang, may not have an answer within general relativity. Not because there was nothing, but because the very concepts of before and after are concepts that live inside time. And time itself, in general relativity, is not an absolute background, but a dimension of space-time woven together with space. And if space-time itself had a beginning at the singularity, then asking what was before it is like asking what is south of the South Pole. The question uses a concept before that the geometry simply doesn't support in that regime. But here is what keeps people working on this rather than throwing up their hands. We know general relativity is incomplete. We know this with certainty because we also have quantum mechanics, which is the most precisely tested theory in the history of science. Its predictions match experiment to better than 1 part in a trillion in some cases, and the two theories are fundamentally incompatible. They use different mathematical frameworks, they make different assumptions about the nature of reality, and in the regime of the very small and the very massive simultaneously, like the singularity, they give contradictory answers. The resolution to this incompatibility, the theory of quantum gravity, doesn't exist yet in any complete form. String theory is a candidate. Loop quantum gravity is a candidate. There are others. None of them is confirmed. But some of them make genuinely interesting predictions about the question we're asking. In loop quantum gravity, for instance, the Big Bang is replaced by a big bounce. The universe before our Big Bang was not nothing, but was a previous universe that had collapsed under gravity to an extremely dense but not infinitely dense state, then rebounded outward in what we experience as the Big Bang. In some formulations of string theory, pre-Big Bang scenarios involve a higher dimensional space with brane structures colliding. In Hawking and Hartle's no boundary proposal, time itself becomes imaginary in the technical mathematical sense at the Big Bang, making the question of before not just unanswerable, but geometrically nonsensical, in the same way that going further south than the South Pole is geometrically nonsensical. I find all of these ideas interesting. I want to be clear that I don't find any of them convincing yet, and I think intellectual honesty requires that I say so. We are at the edge of what we know. The next step requires physics we do not yet have. And the one thing I am confident of, having watched science work for long enough to have some right to an opinion, is that when we do find that physics, when the theory of quantum gravity eventually emerges and its predictions are tested and confirmed, it will almost certainly reveal that the nature of space and time and the very foundation of physical reality is even stranger than anything I am describing tonight. There is a possibility that I want to mention because I think it may be important and I think it doesn't get enough serious attention in public discussions. The possibility that space is not fundamental, that space-time itself, the thing we have been treating as the foundational arena of all physics, is in fact emergent, a derived quantity, something that arises from a more basic underlying structure in the way that temperature arises from the motion of atoms. Temperature feels like a fundamental property of things, and in our everyday experience, it is perfectly adequate to treat it that way. But there is no temperature in the fundamental description. There are only atoms in motion. What if there is no space in the fundamental description either? What if space is something that emerges statistically from the interactions of more basic entities that are themselves not spatial? This is not idle speculation. There are hard mathematical arguments coming particularly from work in black hole thermodynamics and what's called the holographic principle that suggests the information content of a region of space is proportional not to its volume, but to the area of its boundary. As if reality is, in some technical sense, two-dimensional and what we experience as three-dimensional space is a kind of projection. Juan Maldacina's work in the late 1990s made this precise in a specific mathematical context. He showed that a certain theory of quantum gravity in a space with a particular geometry is completely equivalent to, contains exactly the same information as a theory of ordinary particles living in one fewer dimension on the boundary of that space. Not similar, not analogous, exactly equivalent. The same theory described two different ways, one of which has one more dimension than the other. This should strike you as deeply strange, because it is. I have been sitting with it for decades now, and I still find it genuinely disorienting every time I think about it carefully. What it suggests is that dimensionality, the very number of dimensions that space has, may not be a fundamental fact about reality, but a perspectival one. That space, including all three of its dimensions, may be information organized in a particular way. And if that is true, then asking what is beyond space may be asking what is beyond a particular representation, what exists in the underlying information structure from which the representation is built. I don't have an answer to that. I want to be completely clear that nobody has a complete answer to that. But I think it is the right question, and I think it connects our seemingly cosmological question, what is beyond space, to something even more fundamental. The question of what physical reality actually is, underneath all our theories and representations and coordinate systems and measurements. What is the stuff? Not what does it look like from the outside, but what is it in itself? I got my scientific training in a period when that kind of question was considered slightly disreputable in physics. Physics was supposed to be about predicting measurements, about writing down equations that matched experimental data, about the pragmatic business of making the numbers come out right. Questions about what reality is in itself underneath the equations were considered the province of philosophers who were, and I am paraphrasing, an attitude I encountered rather often in my early career, considered to be people who had all the questions wrong to start with. I never shared that attitude. I think it is intellectually impoverished and ultimately self-defeating, because the deepest advances in physics have always come from people who took seriously the question of what was really going on, not just what the equations said, but what the equations meant. Einstein didn't just write down the mathematics of general relativity and call it a day. He thought very hard about what it meant that the speed of light was the same for all observers. He thought about what it would be like to ride alongside a beam of light. He used thought experiments not just as illustrations, but as the actual engine of discovery. The thought experiments came first. The mathematics came after to make rigorous what the thought experiments had already suggested. This is, I think, the correct relationship between physical intuition and mathematical formalism, and I worry that we have lost some of that capacity for deep physical reasoning as the mathematics has become more abstract and more specialized. Let me try to bring this back to something you can hold in your hands for a moment. Think about what it means for the universe to have no edge. I described the balloon analogy earlier, but let me push on it a little harder, because the analogy has a hidden flaw, and the flaw is instructive. The balloon's surface, in the analogy, is embedded in three-dimensional space. A creature living on the balloon could not reach out of its surface and touch the space around the balloon, but the space is there. The balloon has an outside. Our universe, if it is like the balloon surface analogy, does not require an outside. The mathematics of curved spaces developed by Bernhard Riemann in the 1850s, not to describe the universe, but to generalize geometry, and then picked up by Einstein half a century later because it turned out to be exactly what he needed. The mathematics of curved spaces is perfectly consistent without any embedding in a higher dimensional space. The curvature is intrinsic. It can be measured entirely from within. You don't need an outside for a curved space to be curved. What this means, stated plainly, is that the universe can be finite and yet have no outside, no beyond, no surrounding medium it sits in. If you traveled in a straight line in one direction long enough in a finite universe with the right topology, you might eventually return to where you started, the way someone walking in a straight line on the surface of the earth eventually returns to the starting point. You would never reach a wall. You would never find an edge. You would simply find that space closes on itself. And the question, what is outside the universe, would, in that case, be like asking, what is outside the surface of the sphere? The question contains an assumption that outside exists that the geometry simply doesn't support. But notice that this is not the only possibility. The universe might also be infinite. The data we have, the geometry of the observable universe, as measured through the cosmic microwave background, is consistent with the universe being very nearly flat. Flat like a plane, not curved like a sphere or a saddle. And a flat universe that extends in all directions forever is infinite. It has no outside because it has no boundary. There is simply more space in every direction without end. In that case, asking what is beyond space is not a question about what lies outside a bounded region. It is a question that presupposes there is an outside to an infinite thing, which is its own kind of confusion. We genuinely do not know which of these is true. The universe might be finite with a topology we haven't detected because the topology scale is larger than our observable patch. It might be infinite. The observations we have cannot yet distinguish between these possibilities. This is not a permanent ignorance in principle. Future measurements of the cosmic microwave background might reveal patterns consistent with light wrapping around a finite universe, but it is a current one, and I think we should hold it with appropriate intellectual honesty rather than confidently asserting that the universe is infinite or that it is finite, when what we actually know is that our current data is consistent with both. Here is what I want you to take away from everything I have said tonight. The question, what is beyond space, is not a naive question. It is not a question for children or for people who haven't thought carefully enough. It is a question that cuts to the very foundation of what we mean by physical reality, and the honest answer to it has at least 4 layers. First, there is almost certainly more universe beyond our observable horizon, more of the same kind of space, with the same laws of physics, extending to a distance we cannot measure and may never measure. Second, the question of whether space has an edge or a beyond in the geometric sense depends on the global topology of the universe, which we do not yet know. Third, the question of what space is expanding into may be a malformed question, or it may be pointing to a real structure and embedding space, higher dimensional medium that we have no observational access to and may never have. Fourth, and most deeply, the question of what space itself is, what it is made of, whether it is fundamental or emergent, whether space-time is the floor of reality or a pattern painted on a deeper floor. That question is genuinely open, genuinely important, and genuinely one of the most exciting frontiers in physics today. And here is the thing that I think matters most, not just for physics, but for what kind of creatures we decide to be. The temptation, when faced with a question this big and this difficult, is to reach for a premature answer. To say, oh, it's the multiverse, or oh, it's an infinite space, or oh, it was all created at a moment that has no before. And to let the word serve as a substitute for the understanding. I have seen this happen in physics, and it makes me impatient. A word that ends the conversation is not a scientific answer. A word that opens the next question might be. Every time in human history that we have found a true boundary to our knowledge, a real edge to what we understood, the response that has served us has been not acceptance of the limit, but curiosity about it. The darkness beyond the firelight is not a sign that the world ends there. It is an invitation, the fact that we cannot see beyond the cosmic horizon, that our equations break down at the singularity, that our two great physical theories are fundamentally incompatible in just the regime, where the question becomes most urgent. None of this is a reason to stop asking. It is the reason to ask harder. There is something that I find privately extraordinary about the situation we are in. Here we are, creatures who emerged on a small rocky planet around an unremarkable star on the outer edge of an ordinary galaxy. Creatures built from star-forged atoms by billions of years of blind biological process. Creatures who lived in caves not so long ago and killed each other with rocks. And somehow, through an extraordinary chain of accident and effort and curiosity and argument, we have developed the capacity to ask serious, mathematical, empirically grounded questions about the structure of space itself, about what happened at the beginning of time, about whether there is a beginning of time, about what lies beyond what is visible. We can hold these questions and pursue them with rigor. We can be wrong about them and correct ourselves. That capacity, that's not a small thing. That is, I think, the most extraordinary fact about us. The universe is not required to be comprehensible. The laws of physics could have been such that they place their own deep structure permanently beyond the reach of beings like us. They might still be, we cannot know in advance, the ultimate ceiling on what minds like ours can understand. But so far, every time we have taken a question seriously and pursued it with enough imagination and rigor and willingness to be surprised, we have found that the universe is willing to answer, not all the way, not without struggle, but willing. What is really beyond space? Honestly, we don't fully know. And if you think that answer is unsatisfying, I want you to sit with that dissatisfaction rather than resolving it too quickly. Let it push you somewhere, because the history of every great discovery in the physics of space and time is a history of someone who was unsatisfied with the answer that everyone else had settled for. Riemann was not content to assume that geometry was Euclidean. Einstein was not content to assume that simultaneity was absolute. Lemaitre was not content to assume that the universe was eternal and static. Their dissatisfaction was not a personal failing. It was the engine of everything. So don't let anyone tell you that the question has a clean answer yet. It doesn't. And don't let anyone tell you that the absence of a clean answer means the question isn't worth asking. The questions most worth asking are almost always the ones that don't yet have answers. That's not a problem to be solved by finding a comfortable stopping point. That's the actual situation, and the actual situation, as best I have ever been able to determine, is the only place worth standing.